Hello and welcome to the University of York and the Autonomous Robot Evolution Lab, based here in the Institute for Safe Autonomy. Today we're going to show you real robots that have been evolved and constructed by machines. You will get to name the final robot and see it operate in an environment. I'm Andy Tyrrell. I'm an academic in the School of Physics, Engineering and Technology, and I'll be leading you through the exciting world of evolutionary robotics.
Hi, I'm Edgar Buchanan, and I am a researcher on the ARE project, and I'm going to take you on a special tour where we'll see some robots in simulation and how they behave.
Hi, I'm Robert Woolley. I'm a researcher on the ARE project, and I'm going to be introducing the RoboFab, a robot that builds robots. It will assemble one from a 3D printed skeleton and electronic organs.
Today, we're going to show you some of the work of our ARE project, which was funded under an EPSRC grant and includes colleagues from Edinburgh and Napier University, the University of West of England Robotics Lab, and the Free University of Amsterdam. Here in York, we can build lots of different robots, ones that have wheels, have legs, ones that can swim, groups of robots that work together to perform a task, and a lot more. The most important thing is to have the right robot for a given situation. Imagine you're an engineer who wants to send a robot to explore a faraway place, a place whose geography is completely unknown and is likely inhospitable. Mars, for example. Bit of work for you now out there. We're going to ask you to put in the chat box what features you think our Mars robot will need. How do you think it should move? What might it need to sense the environment? Does it need limbs? If so, how many? Put your ideas in the chat box and we'll check your suggestions in just a few minutes. Instead of designing a robot and sending it off in the hope that it will be suitable, what if we sent a robot fabrication facility that figures out the type of robot needed when it arrives, builds it, and then enables the robot to continue to improve itself to adapt to its new environment, to evolve. For example, it might start off maybe with just wheels, like this robot has here, 8 wheels. And then later on, it might find that that's not good enough for that environment. And so maybe it involves one with wheels and sensors and a leg, as we can see on this one. And we'll see more of these later on. That's exactly what my colleagues and I are working on, a radical new technology that enables robots to be created, to reproduce, and evolve over time. A technology where robots' design and fabrication becomes a task for machines rather than for humans. So, Heather, what do we have in the chat box?
We've got suggestions for needing tracks to move across the ground, or lasers to sense the ground as it moves, and cameras to see where it's going. Fantastic.
These are some really super suggestions. But what I think you can see from this is that there's no one solution that will be ideal for all tasks. Thanks for those great ideas. We'll be back on the chat box later. What if I just told you you'd won a mystery holiday and sent you off to pack a suitcase? It could be to visit the pyramids in Egypt, or it could be to visit polar bears in the Arctic Circle. How can you prepare if you don't know the environment you're encountering? This is the issue faced by our Mars robot. We don't know exactly what it will encounter. To pack for every scenario will take us over the luggage limit. So instead, we send it with the tools it needs to make what it requires. And even if the first robot it produces in the new environment, it might not be a perfect solution straight off. And if our robot encounters something new or difficult or even dangerous, it might have to change to evolve. In the similar way to generations of humans and animals have adapted to their situations, robots can also evolve, with each generation better adapted to the environment than they were before. Edgar will now illustrate this idea, but with robots.
I would like to start by describing the task the mission that robots need to accomplish. For this, the robots need to start in one side of the arena and they have to reach the beacon on the other side of the arena. There are a set of ridges in the way which make it impossible for robots with wheels to reach the target. In the video that you're going to see next, you will see the progress through evolution showing a family tree. This video shows a family tree of a robot from its grandparents to its parents to the final child. Robots are aiming to move around the arena to reach the target. The pink lines represent the sensors on the robots. The features of the grandparents alone are not enough to solve the problem, but by combining their genes, new robots are generated with better features and more adapted to the task than the parents. This process is repeated multiple times until the final desired robot is created, the child in this case. Slowly, over time, evolution creates robots with legs. An analogy is that for a long time, people used to write with ink. Then people started to use typewriters, then PC, and more recently, using touchpads and phones. Slowly, over time, the technology is evolving. Back to Andy, who is going to start making a robot.
So let's start making some robots and then see how they might evolve. Let's start the printer for a new skeleton, Rob, please. So we started this print a while ago because it typically takes around 3 hours for the print to print a full robot skeleton before we can then move on to building a complete robot, which we're going to show you pretty soon. We will pause it again now since it's quite noisy. Remember, this skeleton, however, has been created through evolutionary evolution. Surprisingly, artificial evolution needs just 3 main components. A population in which individuals exhibit some physical variation, a method of reproduction in which offspring inherit traits from their parents, as Edgar has just described, and sometimes acquire new traits through mutation or random changes. And finally, selection. This will typically loop many times before a suitable robot is created. Edgar is now going to talk about robot DNA.
The first step is to design a digital version of the DNA that describes what the robot body and the brain should look like, including its skeleton, its sensory mechanisms, and its means of locomotion. In the video that you're going to see next, digital and physical versions of the robots with the same DNA are shown. The video at top shows a virtual version of the robot, and the video below shows a physical one. Even though both robots are represented by the same DNA, both robots behave differently due to differences between the simulation and the reality. Now over to Rob, who is going to tell us how the blueprint is turned into a real robot.
So we've designed this technology that transforms each blueprint into a physical robot without the need for human help. It first uses the 3D printer, as you saw earlier, to create a skeleton, right? And then the brain would pull that off the print bed and put it into the assembly stand. We skipped that bit and just went straight to the assembly stand where it's going to start putting some organs on. Okay, so first it's going to pick up central organ, which I'll talk about in a bit more detail in a bit. It grabs it by the cable and moves it towards the assembly stand. Okay, so each action we programmed in using this UR5 robot arm. So first it's going to line up above it and then use our designed slide clips to attach it to the skeleton. Each have like a small spring mechanism in them that allows them to attach and stay on. Okay, so it's going to slide in now, and then it's going to pull the cable out from the organ, which allows it to connect to the brain or the processor or the main like computer, as you might say, of the robot, and it lets go, and then it's going to go back to the organ bank to collect another organ. This process will repeat over all the parts needed for the robot. And at this point, it's going to pick up a different sensor and put it in a different place. You can see the assembly stand turns so that it's easy for the robot arm to access where it has to place the next one. And here it is picking up the second organ. We're just going to show two of them now before showing a video of some other ones going together. So here it's then picked up by the cable. You notice also we use these coily cables, that means they're out of the way when the robot's moving around. And here it is going over, lines up, moves down to clip in, and then it's going to connect the cable. Okay? So each of these have a different address, which allows them to talk to the main body of the robot. And it clicks in, you can hear it click. It's going to unhook the cable and plug that into the main body of the robot. And then I'll pass it to Edgar, who's going to explain a bit more about complete robot build.
Thank you, Rob. In the next video that you're going to see next, the process is speeded up 8 times, and you're going to see the robot fab assembling a complete robot. The robot arm takes an organ from the organ bank and connects it to the skeleton. Then it connects the cable from the organ to the brain of the robot. This process repeats for every single organ in the robot. The robot is held secure at the assembly fixture with electromagnets. And this assembly fixture has the capability to rotate, which grants access to the robot arm to connect all the organs from all directions. The process of fabrication takes between 2 and 5 hours. The time is dependent on the shape of the robot. Most of the time is spent printing the robot, and the assembly takes roughly between 5 and 15 minutes. Here we have it. We have a new robot. We need a name for this robot. How should we call this robot? Put your suggestions in the chat box, and we pick a winner for the final robot today. Rob, tell a little more about the physical robot and the different components and organs.
So there are 3 main components to our robot. And to make things easier, both for our tracking system and for you guys, we've color-coded them. First, we have the brain, which is the middle of each robot. We've colored that red. That involves a Raspberry Pi at the core, which acts as a computer. It also has a battery, camera, fans, and also all the connectors needed, like the headphone jacks to go into. Next is the green skeleton. And this is 3D printed, as you saw earlier, and that gives a shape to the robot. It also has all the clips where the organs attach and orientate themselves. So you can have almost any shape or direction of your different parts of your robot. And finally, the blue parts are the various organs within, which are the main electronic parts. There's 4 of those in total. 2 of them for locomotion. First, we've got a wheel, which is a little metal gear motor in here, controlled by an Arduino with an encoder, and that basically gives it a drive, allowing the robot to move forward or around the arena. Next, we have a servo inside the case, which is able to give a different form of locomotion if the robot needs to climb over things. The final electronic part is the sensor, which actually there's 2 sensors in here. First, a laser for distance measuring, so it can sense the obstacles around itself, as well as a passive IR sensor, which is able to detect the beacon as it flashes in infrared. Finally, we have a purely mechanical organ, which is called caster wheel. So it's got a ball on the bottom, which is able to slide across the arena, so it doesn't get stuck on them. All of them have this sprung mechanism clip, which allows them to be connected to the main skeleton. Back over to Edgar, who's going to explain how robots learn.
Right, so we know how the shape of the robots is created in simulation and how they are fabricated autonomously. But what about the brain of the robot? To give the brain, a neural network in this case, a chance to adapt to its new body, we send each new robot to the equivalent of a nursery for a short period of time, where it undergoes a learning process to fine-tune its motor control. In the video that you are going to see right now, shows 4 different stages of the learning process in simulation. At first, the robot is not very smart, and it's doing this kind of random movements, and is struggling to move towards a target. However, after a few generations, the robot becomes smarter, until the robot is able to reach the target, as it is shown in the bottom right video. If we leave a robot to learn for a few hours, days, weeks, it would be ready to take on more complex tasks. But what if we are in a hurry? Let's say that there has been a mining accident on Mars and people need help right away. We don't have time to play with hundreds of robots, so we put virtual robots in a virtual nursery. We have a digital version of every new Evolved robot in simulation and allow these virtual robots to learn purely in simulation. This allows us to quickly explore the potential of a wide range of robot types and get a rough estimate of how useful they might be. Back to Andy to name our robot and get it moving in the arena.
Great, thank you, Edgar. So Heather, do we have a name for our robot?
We've got Marvin.
Marvin.
There you go.
Thank you. Excellent name. Very good. Let me give that to Rob to put on our robot ready to go into the arena. Thanks, everybody, for those suggestions. So we predict that by allowing breeding to take place between a physical robot and one of its virtual cousins, useful traits discovered in simulation can quickly spread into the real robot population, where they can be further refined in situ. So here you can see a robot that has had its body plan evolved and then constructed in the fab, a simple controller downloaded to its brain, and some time for the brain to learn and improve in its environment. It's looking for a beacon or maybe a lost robot on Mars. Robots clearly have a role to play in our future, in the applications ranging from revolutionizing healthcare to undertaking tasks too difficult for humans, as well as helping us pursue scientific quests for exploration on Mars, for example. Perhaps digital evolution can also help address some of the issues associated with designing robots right here on Earth. So there we have it. How do you get the perfect robot for every situation? You build it, you let it build itself and to learn. So if you did ever win a mystery holiday, perhaps the best thing you could pack would be a 3D printer. That's the end of our demo. Thank you for coming along today. I don't know if we have time for a couple of questions, Heather?
2 questions. The first one is, would it be possible to build the skeleton from material other than plastic?
Okay, yeah, no, that's a really good question. So actually the DNA that Edgar talked about previously, it doesn't care what the material is that we're printing. So if you've got a printer that maybe would print metal, there are 3D printers that would print metal, then absolutely, you could use that then for printing a metal one, or any other material that your 3D printer happens to be able to print.
Okay, and the second question is, can you tell us how far these evolving robots are from commercialization, as this could bring a really positive impact to places on this planet that aren't easily accessible?
Okay, yeah, really excellent question. And so one of the applications we've got on for our planet will be things like nuclear caves and things where they've got, so exactly along those lines. So I would say we're quite a long way away from commercial exploitation at the moment. But I think what we've done here is we've proved the principle. So we prove that we can evolve robot bodies and brains, which nobody else has tried before. So we're actually at a point now where absolutely we can move towards commercialization in the future. Okay, thank you very much, everybody.